On the morning of December 8th, 3E Atlas ignited not with heat, not in a burst of energy, but with a brilliance that was stark, immediate, and unmistakable. The phenomenon began with a sudden spike in brightness. For nearly 3 weeks, this mysterious interstellar object had followed a steady pattern, its light gradually dimming as it drifted farther from the sun. Exactly as expected, but as it crossed into a critical orbital vector, slowly drifting into Earth's observational corridor, something changed. The object's light curve surged. Its albedo, or reflectivity, soared with unexpected intensity. Instruments in Chile, Japan, and the Canary Islands all recorded the dramatic event. The surge lasted just under 4 minutes. Then, almost as swiftly as it appeared, the light faded back to baseline. This wasn't a typical cometary flare. There were no signs of fragmentation, no sudden bursts of volatile gas, no blossoming dust tails or trails of materials scattered from the nucleus. In fact, the coma remained disturbingly steady, almost unnaturally so. This wasn't the erratic outburst typically seen when heat triggers cracks or surface fractures. It was calm, controlled, and geometrically perfect, almost as if the object's surface had been deliberately turned or adjusted. Amateur astronomers, initially baffled, speculated that the spike might be some kind of observational anomaly, perhaps interference from a nearby satellite or Earth's atmosphere. But then, the same flash was confirmed by long baseline instruments across multiple observatories. It was not a local glitch, nor was it random. 3 independent observatories, operating independently without coordinated schedules, recorded the exact timing to the second. What makes this ignition so perplexing to astrophysicists is that it broke all the rules of celestial mechanics. Normally, solar heating causes sublimation. Sublimation causes venting. Venting leads to brightening. It's a predictable, well-understood chain of events. But this event didn't follow any of those patterns. The solar flux at the object's location hadn't changed significantly. Radiation pressure was, in fact, diminishing, not increasing, and there were no signs of gravitational interference from any nearby bodies. The ignition appeared to have been spontaneous. Yet, when analysts sifted through high-speed imaging and infrared logs, something curious appeared. Just before the brightness peaked, there was a localized fluctuation in the light curve, a brief dip, a sharp rise, and then a leveling out into a plateau. The shape of the curve was unlike anything we'd expect from a comet or asteroid. It looked more like a controlled reflection, the kind you'd see if a surface were rotating, flattening, or unfurling. More intriguingly, no heat signature followed the flash. Typical cometary ignition events release thermal energy as they flare. This one did not. The infrared profile of the object remained cold, even at the peak of its brightness. If this had been caused by a flare-up of carbon dioxide or water vapor, the instruments would have picked up thermal radiation spilling from the coma. But instead, the spike was purely visual, a light show without the accompanying heat. And that's when researchers began to use a new word to describe the phenomenon: response, not reaction. The flash didn't behave like a symptom of heat or pressure, it behaved like an answer, a signal. Almost immediately, the flash was followed by a secondary anomaly, a slight but measurable shift in the object's trajectory. The change wasn't enough to dramatically alter its course, but it was enough to register a deviation from previous models, a subtle outward push, not from the sun, but in a direction angled toward deep space. The timing was far too precise, the shape of the curve too clean. A cause and effect relationship began to form. The object brightened, stabilized, and then nudged itself ever so slightly, almost as if it were recalibrating itself. This wasn't the chaotic burst of activity we'd expect from a comet. This was something far more deliberate, and this raises a troubling question that most astronomers are reluctant to vocalize. What kind of interstellar object waits until it's past the Sun, past Jupiter, and approaching Earth before it ignites? And, more perplexingly, what exactly did it ignite not long after the ignition faded? Another anomaly emerged, one far more difficult to explain and even harder to dismiss. 3 Atlas began to accelerate, but it wasn't a violent, sudden burst. Instead, it was a steady, measurable acceleration, an increase in speed without any of the usual mechanisms we rely on to explain motion. At first, analysts thought it might have been a recalibration issue. After all, interstellar objects are difficult to track with precision, especially as they move farther into space and telescope signals grow weaker. But when both the Pan-STARRS network in Hawaii and ESA's solar orbiter independently confirmed the same deviation, the data became undeniable. The object was gaining speed, but nothing was pushing it. This sudden acceleration didn't follow any known cometary outgassing patterns. There were no visible jets, no expanding gas cloud, no surge of carbon monoxide or carbon dioxide, the typical suspects that serve as internal engines in traditional comets. In fact, the object's spectrographic profile showed an unexpected absence of volatile activity. If anything, the object had become quieter since the ignition event, yet its trajectory was shifting. The nature of this acceleration was just as curious as the event itself. Instead of the usual radial push directly away from the Sun, 3 Atlas seemed to curve slightly off-axis, following a path angled toward Earth's orbital trajectory. But even more puzzling was that the acceleration wasn't random. It followed a clean, continuous arc. There was no chaotic wobble, no rotational disturbances. The object's movement was fluid, controlled almost like it was under intelligent guidance. That's not how natural bodies behave in open space. When comets outgas, they do so unevenly. One hemisphere often receives more sunlight than the other, leading to irregular jets of gas that push the body unpredictably. These jets usually cause wobble, brightness shifts, and heat imbalances. But 3 Atlas exhibited none of these behaviors. Its brightness remained stable, its rotation showed no significant changes, and its thermal profile remained flat. Yet, its course was changing. Scientists call this type of movement non-gravitational acceleration, a shift in trajectory not caused by the gravitational forces of planets, stars, or moons. Typically, non-gravitational acceleration is explained by sublimation, the gradual release of gas that acts as a weak thruster, but that explanation doesn't hold here because the spectral data showed no significant outgassing. The object was eerily quiet. Early on, one theory was that mass shedding had occurred. Maybe a small fragment of the object broke off, altering its momentum, but no debris was observed. No dust plume followed. There was no sudden drop in temperature that might suggest a fracture. The object remained intact. So, what caused the shift? Some researchers suggested solar radiation pressure, the gentle force exerted by photons on a reflective surface. This explanation fit with some of the readings. But there was a problem with the scale. For radiation pressure to cause such a large deviation in trajectory, the object would need to be extremely light, extraordinarily reflective, or both. But that doesn't fit the profile of a typical comet. Comets aren't flat, smooth, or designed to catch sunlight like a solar sail. But if 3 Atlas was somehow constructed, or simply had geometric properties that mimicked a solar sail, then this kind of acceleration starts to make more sense. And the most curious part of all, this acceleration didn't begin near the Sun, where radiation is most intense. It started much farther from perihelion. After the object had already passed out of Jupiter's gravitational influence, it was almost as if the object had been waiting, like it had carefully planned its next move. The nature of the acceleration clean, smooth, and unaccompanied by dust, gas, or noise doesn't match anything we've seen in our catalogue of cometary behavior. If the object is reacting to sunlight, it's doing so in a way no natural body has ever been observed to do. And if it's not reacting, but actively responding, then we're no longer talking about passive physics. We're talking about behavior. To understand this behavior, we need to go back not just to the Sun, but to Jupiter, before the object ignited, before it accelerated, and before it altered its course toward Earth. It had already passed close to the most powerful gravitational force in the solar system, other than the Sun, Jupiter. Jupiter's gravitational field is immense. It doesn't just capture moons and asteroids, it shapes entire orbital families. Some comets spend their entire lives trapped in looping trajectories because of a single close pass by the gas giant. Others are flung entirely out of the solar system, sent spiraling away by Jupiter's immense mass. When an object like 3 Atlas, already traveling at interstellar speeds, passes through Jupiter's sphere of influence, it's an event worth watching, and astronomers were certainly watching. Their calculations had predicted the flyby weeks in advance. It wouldn't be close by planetary standards, about 2 astronomical units from the gas giant, but it was close enough for Jupiter's gravity to have a measurable effect. And it did. Sort of. Data from NASA's JPL in late November showed a small but classic gravitational nudge. It wasn't anything dramatic. Just a slight bend in the path, well within the expected range. But when the same data was reanalyzed after the ignition event of December 8th, something strange appeared. The timing, the curvature in the trajectory didn't begin at periapsis, the point of closest approach to Jupiter, as we would expect. Instead, the deviation began several days later. Even more peculiar was the way the trajectory curved. It wasn't a smooth arc, as we'd expect from a gravitational slingshot maneuver. Instead, it was a sharp cutoff, as though the influence that had been acting on the object had suddenly ceased. Even stranger was the nature of the deviation. When 3 Atlas passed into Jupiter's gravitational sphere, analysts noted a brief oscillation in its trajectory model. The object's orbital solution jittered. This wasn't a mechanical glitch. The software was detecting subtle shifts in velocity, small variations that didn't align with the predictable patterns of a passive flyby. It was as though 3 Atlas had resisted Jupiter's gravitational tug, had stabilized itself against its pull, then paused, because just 3 days after that gravitational window closed, the ignition event occurred, marking an eerie connection between the two. Some scientists dismissed the timing as mere coincidence, a random alignment of events, but others, far more cautious, weren't so sure. At the Max Planck Institute, a team of dynamicists ran reverse simulations of the flyby, modeling it under dozens of different gravitational assumptions, varying mass estimates, spin states, tail effects, even hypothetical outgassing. Yet, no matter the adjustments they made, the results still didn't match. Something had delayed the response to Jupiter's influence. Something had inserted a pause. The simplest explanation would be inertia, a delay caused by the object's motion being slow enough that the deviation took time to manifest. But 3 Atlas is moving at over 200. Nulla came, that kind of delay shouldn't exist. Not with that speed. This led to a different possibility. What if 3 Atlas didn't respond immediately because it wasn't ready to? What if the object had waited until it was far beyond Jupiter's gravitational reach, biding its time before taking the next step? What if it recognized the end of that influence and triggered the ignition at that precise moment? In astrophysics, trajectory planning often involves burn points, precise moments when a spacecraft fires its engines after a flyby to take advantage of a planet's gravitational pull. The fact that 3 Atlas ignited just after leaving Jupiter's gravitational grasp suggests a level of synchronization and intentionality that's hard to explain through natural behavior alone, not because Jupiter directly caused the ignition, but because its absence might have allowed it. There's a pattern emerging in the behavior of 3 Atlas, and it has less to do with what it emits and more to do with what it reflects. On December 8th, mere moments before the object began accelerating, astronomers observed another strange event, a sudden spike in reflectivity. It lasted less than 4 minutes, but the change was unmistakable. The object, which had been exhibiting low, stable brightness across multiple spectra, suddenly flared not from heat, but from light. This wasn't heat. This was light. A flat, cold glow that didn't match any known model of outgassing, fragmentation, or thermal emission. The spike had all the hallmarks of specular reflection, the kind that occurs when light bounces off a smooth, mirror-like surface. And it wasn't the first time something like this had happened. Back on October 29th, During perihelion, the closest point in 3 Atlas's orbit to the Sun, a similar event had been recorded. At that time, the spike was dismissed as a thermal anomaly, perhaps caused by a sudden venting of gas or a fracture in the crust that exposed fresh ice. But now, in hindsight, the December event appeared to be a mirrored repeat of what happened near the Sun. Same brightness pattern, same duration, same absence of thermal radiation. In both cases, the object didn't heat up. Instead, it simply became more reflective. And then, as quickly as it brightened, it dimmed again, almost as if a surface had tilted or shifted. This comparison has led scientists to re-examine the flare near the Sun at perihelion. Solar observatories, including SOHO and the Parker Solar Probe, captured what appeared to be a flash, an instantaneous increase in visible brightness. The explanation offered back then was sun-induced outgassing, but that too lacked corresponding emissions. There was no infrared spike, no sudden blooming of a tail, just clean, directional light. And now, it's happened again. But this time, the Sun isn't nearby. The December event occurred at more than 6 astronomical units from the Sun, far beyond the region where typical thermal flares occur. Solar radiation pressure is still present at that distance, but it's greatly diminished. The solar flux simply isn't strong enough to induce such an optical surge in a normal object. Yet, the reflectivity spike did happen, and that's where things get even stranger: the angle of the light. In both October and December, the geometry of the spike, the direction in which brightness increased, aligned precisely with the angle of solar incidence. That is, the object brightened most intensely when the light struck it from a specific direction, suggesting a highly reflective surface, a deliberately aligned structure, not a chunk of tumbling ice, not jagged rock face, a panel, to a surface. When researchers plotted the timing of the spike against the object's known rotation period, they uncovered something unsettling. The flare occurred at nearly the same rotational position both times, which implies this wasn't a random reflection. It was a controlled orientation. Something on the object had turned to face the light source once at the Sun, and once again, facing Earth's orbital path. This behavior has no precedent in natural comet physics. Natural bodies, with their irregular shapes, can cause brightness variations. Yes, but not with this level of precision, symmetry, and timing, and certainly not without corresponding changes in infrared emissions or volatile output. Even more intriguing, the brightness spike on December 8th began just 36 seconds before the object's velocity vector shifted. The reflection came first, then the acceleration. The sequence isn't just suspicious, it's deliberate. In engineering terms, this is equivalent to a sail deploying just before a solar push. Not a reaction, but a planned event. So the question remains, what kind of object maintains a mirror-like surface orientation over tens of millions of kilometers, and then uses that reflection as part of its propulsion? If this isn't natural, it may well be something far more advanced, not emitting energy, but simply utilizing what's already available. The ignition event had barely settled before something even stranger appeared, a shift not in light, but in sound. Not sound in the traditional sense, but in the subtle frequency distortions that astronomers use to measure motion in space. This is known as the Doppler effect, a tool so fundamental to astrophysics, it's used to track everything from exoplanets to spacecraft. And when applied to 3 Atlas, it revealed something that made radio technicians stop mid-sentence. The signal was moving the wrong way. In early December, the Querétaro Inter-American Observatory in Chile began a coordinated radio campaign with 2 other facilities, the Green Bank Telescope in West Virginia and a Japanese ground station specializing in passive radar detection. Their goal was simple: track any changes in the reflected signal strength or timing as 3 Atlas moved deeper into Earth's observational corridor. Under normal circumstances, a comet or asteroid moving away from Earth will produce a downward shift in the return frequency, a classic Doppler redshift. But the radar echoes they recorded told a different story. For several minutes, during the same window as the ignition, the The reflected signal from 3 Atlas narrowed, then subtly bent toward the blue end of the spectrum. In layman's terms, the object gave off a brief indication that part of its surface was moving toward Earth, or at least toward the detectors faster than predicted. But here's the catch. The observed shift didn't come from the tail, where outgassing or trailing particles would logically originate. It came from the leading edge, the forward-facing section, the nose. In comet science, that's unheard of. If a natural object experiences outgassing strong enough to influence motion, the emissions typically emerge from the sun-facing side. That vapor is then pushed outward, trailing behind the comet and accelerating it in the opposite direction. But the Doppler data shows the opposite, a forward motion, as if something at the front of 3 Atlas initiated the change. One early theory proposed a forward-facing gas jet, but that doesn't make physical sense. Solar radiation should suppress forward emissions, crushing them with the very photons accelerating the object. Others suggested the possibility of a rotating reflective surface, perhaps a mirror-like structure, periodically aligning with Earth's line of sight, causing the signal bounce to appear shifted. But the frequency change wasn't oscillating. It wasn't rhythmic. It was clean, deliberate, a sharp shift, followed by silence. Even more baffling was the intensity curve. The strength of the radar return increased just before the frequency shifted, then dropped again almost instantly. That profile doesn't match ice, rock, or dust. It matches high density, compact materials, the kind used in engineered reflectors, not in porous comet nuclei. When the 3 facilities compared timestamps, they confirmed something else. The anomalous Doppler shift aligned precisely with the same window in which the object's brightness surged and its trajectory changed. 3 different datasets, visual, kinetic, and radio, all pointed to the same moment. Something happened, something measurable, and it was focused at the object's front. If the shift had occurred near the tail, we'd call it acceleration. If it had happened along the flank, we might blame rotation. But because it came from the front and without any visible emissions, the event breaks every rule we use to describe motion in space. There's only one scenario where this behavior makes sense: controlled propulsion, not venting, not ice, not dust, a directed impulse pushing forward, leaving behind a subtle signature, one that scientists are now calling too clean, too synchronized, and too directional to be explained by chance. Because nature doesn't send signals like this, but something else might. As 3 Atlas continued its post-perihelion journey, the world's most powerful solar observatories were watching closely, but what they recorded on December 8th, during the same window as the ignition and trajectory shift, wasn't a tail, wasn't a flare, and wasn't a jet. It was something else entirely, a halo. At exactly 0422 UTC, ESA's solar orbiter captured a high-contrast visual anomaly using its heliospheric imager. For a brief 90 seconds, a faint arc of light appeared around 3 Atlas, not behind it, like a typical dust tail, and not around the sun. As in a solar halo, this formation was centered around the object itself, like an atmosphere that shouldn't exist. The shape was narrow. It didn't radiate outward like a gas cloud. It didn't stream like a trail. It hovered, static and symmetrical, displaced slightly to the left of the nucleus. The brightness peaked along the edge, with a soft inner gradient that didn't match any known sublimation or scattering models. Most comets, when active, produce visible tails, sometimes 2, a dust tail that curves due to orbital motion and solar radiation, and an ion tail that points directly away from the sun, sculpted by the solar wind. But here, there was no tail, none, no directional stream, no extension, no plume, just a silent, hovering arc with no explanation. What made this halo even stranger was its timing. The glow appeared minutes after the Doppler shift, right after the brief burst of reflectivity, and vanished almost instantly, not gradually, as would be expected from dust dispersal or gas diffusion. Instead, it blinked out of existence like a switch had been flipped. At first, Scientists suspected a reflection artifact, perhaps an internal lens flare or a false positive from sunlight scattering across the camera sensor. But then, confirmation came from another source, the Canadian Space Agency's NEOSat, operating in a different observational band, caught the same event from a different angle. It wasn't an artifact. It was real. The halo existed. Now, the question was, what caused it? Some astronomers proposed that the halo was a detached gas shell, perhaps a rapidly expanding emission of carbon dioxide or fine dust ejected during a sudden internal fracture. But there were problems with that explanation. First, the halo didn't expand. It stayed rigid in diameter for the full 90 seconds it was visible. Second, it didn't disperse. And third, and perhaps most importantly, it wasn't centered. It was offset from the nucleus, trailing behind by a fixed margin. That detail, though small, changes everything. In physics, when an emission is offset from a mass, it implies motion separation. If the halo had come from the object itself, it should have radiated outward in all directions or followed the object's momentum. But this arc didn't trail. It followed. It matched the object's velocity and then disappeared just as the ignition signature ended. That's not a coma. That's not a dust plume. That's something moving with the object and vanishing when it no longer serves a purpose. Speculation began immediately. Was this a temporary energy field, a release of ionized material that reflected ambient sunlight for a few seconds, or something structural? Perhaps a deployed panel, an extended surface, or a shroud reacting to solar pressure. Engineers from the European Southern Observatory quietly suggested another possibility: a reflector, a surface, perhaps angled or curved, that caught sunlight and flared once in view of Earth's orbital plane, something engineered or at the very least unnaturally smooth. Because halos don't form without cause. Comets don't produce glowing arcs in the dark side of their trajectory. It doesn't make headlines. It doesn't trend on social media. But in the world of astronomy, polarization data can reveal far more than what brightness alone can show us. On December 8th, multiple observatories picked up something that few scientists expected to see again. It returned: negative polarization. That peculiar signature first recorded during perihelion, when 3 Atlas flared near the Sun, reappeared once more. But this time, the Sun wasn't nearby. And yet, the signature repeated almost exactly, in depth and shape. To fully understand the significance of this, we need to break it down. When light strikes a surface, some of it becomes polarized, meaning the waves align in specific directions depending on the material, the angle, and the structure it reflects off. Astronomers use polarization data to infer the texture, particle size, and surface composition of an object. Most comets display predictable patterns of polarization, a low degree of polarization at small phase angles, which gradually shifts to positive as the viewing angle increases. This is called the negative polarization branch, and it's a well-understood phenomenon. But 3 Atlas has never followed that pattern. During perihelion, its polarization dropped deeper and more sharply than any comet observed before. Researchers recorded values plunging below -2 by 500T, a level far more intense and focused than any known dusty surface should allow. That was strange enough on its own. But now, this peculiar pattern has occurred again after perihelion, far from the Sun, and under cold space conditions where most cometary activity should have faded. On December 8th, as the object brightened and accelerated, the polarimetric signature repeated almost identically to the one seen back in late October. Recorded by both the European Space Agency's polarimetry imager and an independent team at the South African Astronomical Observatory, the signature came and went within 3 minutes. This time, the light wasn't just polarized, it was reversed again. Negative, clean, and consistent across both detectors. This immediately tells us something significant. This wasn't random. It wasn't a mere observational angle or a temporary scattering of dust. This was structural. Something on 3E Atlas is reflecting light in a manner that suggests a smooth, compact, possibly metallic surface and it's doing so consistently at two very different points in its solar journey. Such consistency is difficult to explain using natural models. A comet's surface is usually chaotic. Irregular outgassing causes jets, fractures, and rotating clouds of dust. Even the most well-preserved comets are riddled with cracks, ice pockets, and loose regolith. This is why most natural comets exhibit erratic, noisy polarization curves. But not 3E Atlas. 3I Atlas polarizes light as though its surface is coherent, tightly grained, and engineered. Some scientists have proposed that exotic materials like graphite-covered ice or carbon-enriched grains could explain this behavior. But even these theories don't account for the repeatability of the signature. Material composition across a comet can vary, especially over time. So, how is this object producing the same exact polarization profile weeks after passing the Sun, after its velocity changed, and after re-entering a colder phase of its trajectory? The only clean explanation is that its surface hasn't changed. It's not chaotic. It's not fragmenting. It's stable. This raises uncomfortable questions. In comet science, stability is abnormal, surfaces erode, spin states shift, and reflected light changes as sublimation reveals new layers. But 3 Atlas is showing us the same optical fingerprint again, a fingerprint that, in human terms, resembles a mirror angled precisely at a light source. And this time, the light source wasn't the Sun, it was Earth. What kind of object reflects light the same way near the Sun, and again near Earth's orbital path, with the same sharp angles, the same narrow polarization, and the same inverted signature? That's not a rock. That's not ice. That's design. For weeks, 3 Atlas had been silent in the radio spectrum. No emissions, no reflections, no static, just a cold, dark signal void, exactly what you'd expect from a natural object moving through deep space. Even at perihelion, when solar activity was at its peak and the comet-like body passed through electromagnetic turbulence near the Sun, not a single coherent signal had been detected until now. On the morning of December 8th, as the object ignited, brightened, and shifted its course, something else happened. Something almost no one saw coming. A pulse. Short, isolated, and unmistakably artificial in cadence. It occurred at 042413 UTC. The Meerkat radio array in South Africa picked it up first, a burst in the megahertz band, just below the FM radio range. The pulse lasted less than half a second. At first, the system flagged it as noise, perhaps solar interference, or a stray background transmission from Earth. But after cross-checking the data, it told a different story. At almost the exact same time, the Murchison Widefield Array in Western Australia logged a similar burst, detected from a different angle, with a different antenna, but in the same frequency band, lasting less than 1 second. Both signals shared an identical temporal profile, a sharp rise in intensity, an ultra-flat plateau, and then a sudden drop-off. No echo, no tail, no repeat. This wasn't background radiation, and it didn't come from the Sun. Triangulation placed the source within a 4.0 kilometer cone, centered around the known coordinates of 3 Atlas. But what made the pulse even more suspicious was when it happened. The signal emerged within seconds of the object's brightness spike, and just before the sudden trajectory shift. In other words, the radio pulse wasn't random. It was synchronized with the ignition event. No known natural body produces this kind of behavior. Comets don't pulse in radio bands. They don't emit compact, highly coherent signals. They don't go silent for months, then suddenly generate a signal that shows up across multiple arrays halfway across the planet. Still, scientists scrambled for conventional explanations. Could this have been a reflection of Earth-based transmissions off the object's surface? Maybe a stray signal bounced off a smooth patch of ice? Unlikely. Extremely unlikely. For such a reflection to occur, the object's surface would need to be smooth and reflective at the megahertz range, and precisely oriented toward two separate receivers. one in South Africa and one in Australia, at the exact same moment. The alignment required is so tight that it borders on mathematically impossible, especially for a body tumbling randomly through space. Then there's the frequency itself. The pulse occurred at just over 42 megahertz, not a common band for satellite interference, not part of the sun's typical outburst spectrum, and not used by most Earth-based equipment outside of military or specialized scientific research. And the waveform, it was clean. Too clean. No distortion. No harmonics. No Doppler stretch. It behaved more like a deliberate ping than an echo. Some radio astronomers quietly raised the most provocative possibility that the signal originated from 3 Atlas itself. If that's true, it changes everything, because a signal that appears at the same time as a reflectivity spike follows a sudden trajectory change and coincides with a rise in negative polarization isn't just a coincidence anymore. It's a sequence. Brightness, acceleration. Radio burst like a machine powering on, like a system running a check, like a beacon aimed back toward where it came from, or toward where it's going next. No one is calling it communication, not officially, but after months of silence, the fact that 3 Atlas chose that exact moment to break its radio silence means something, even if we don't yet know what. When a comet survives perihelion, the closest point to the sun in its orbit, astronomers always look for one thing: damage. The sheer amount of solar radiation and tidal stress encountered near the sun is enough to stress even the most stable bodies. In most cases, it's not a question of if something breaks, but how much. So when 3 Atlas emerged from perihelion intact, scientists were intrigued. When it showed increased brightness and acceleration weeks later, they were stunned. And when high-resolution imaging failed to show a single sign of fragmentation or debris, the conversation changed completely. This simply shouldn't be possible. The expectation was simple. Thermal stress and outgassing should lead to cracks in the surface, even on the most well-bound cometary nuclei. Microfractures, trailing dust, loose chunks of ice. These are all common in even the smallest cometary events. Some comets survive perihelion only to shed mass weeks later. Others disappear entirely, leaving only ghostly trails of vapor. But 3 Atlas shows none of that. In the days following its ignition event on December 8th, observatories around the world turned their instruments toward it, expecting to find evidence of disruption debris, plumes, secondary objects, a faint dust arc. Instead, they found nothing at all. The coma remained tight and symmetrical. The nucleus, still unresolved visually, showed no shadow trails, no particulate haze, and no new optical signatures in the infrared. The tail, already faint, did not bloom or disperse, and the wake remained razor-thin. Even amateur astronomers noticed it in stacked exposure frames taken from observatories in Arizona and Italy. Time-lapse composites showed a single coherent path. No fragmentation spikes, no parallel light trails, and no trailing bodies drifting behind. That's when teams at the Very Large Telescope and the Subaru Observatory performed a coordinated spectroscopic sweep. Their findings: no signs of recently freed volatiles, no shift in dust to ice ratios, no scattering patterns consistent with fragmenting structures. In other words, 3I Atlas hadn't lost anything. This isn't just unusual, it's unprecedented, because we know the forces it's endured. Back in late October, 3 Atlas passed through solar wind densities high enough to scramble magnetic field readings on the Parker Solar Probe. It encountered a coronal mass ejection powerful enough to warp nearby plasma currents, and yet it emerged untouched. Then it passed near Jupiter, where even a subtle gravitational interaction is known to fracture unstable objects. Again, no debris. And now, after a spontaneous ignition, an acceleration event, and a brief radio pulse. Still nothing. No dust, no ice clouds, no microtrails of carbon compounds, just silence. Natural objects, especially those moving at interstellar velocities, are supposed to fall apart under this kind of pressure. That's what we've always seen. That's what the laws of thermodynamics sublimation, and orbital mechanics have told us to expect, but this one hasn't fractured. It's held, so either it's made of something we don't understand, a material that doesn't behave like ice, dust, or rock, or it's constructed in a way that distributes stress evenly across its structure. A geometry that absorbs heat without shattering. A design that survives the Sun and Jupiter without shedding mass. That's not typical cometary behavior. That's stability under intent. And that's why many in the scientific community are now asking a different kind of question. Not how did it survive, but was it ever supposed to break at all? Because if an object can pass through the Sun's wrath, resist Jupiter's pull, and ignite without shedding a single piece of itself, maybe it's not surviving. Maybe it's executing. On December 8th, just as 3 Atlas began exhibiting its most extraordinary behavior, the ignition, the acceleration, the reflectivity spike, the most advanced telescope ever built was watching. And then it wasn't. The James Webb Space Telescope had been scheduled for a mid-range pass observation of 3 Atlas in the early hours of UTC, using its NE-SPEC and MIR instruments to capture detailed spectral data. The goal was simple: gather high-resolution infrared imagery to help determine the object's composition as it moved farther from the Sun and deeper into Earth's outbound corridor. But something disrupted that plan. The official observation log from JWST shows a brief but critical window of missing data, a 6-minute blackout, during which no usable return was recorded. The error was flagged as a possible loss of line of sight due to Earth's umbra interference. But that explanation doesn't hold up under scrutiny. JWST's orbit places it far beyond Earth's shadow. In a constant solar orbit near the second Lagrange point, nearly 1.5 million kilometers from Earth. This is precisely why the telescope was positioned there to avoid Earth-based obstructions. And yet, the observation cut off at the exact moment 3 Atlas entered a brief geometric alignment between Earth and JWST. That timing, down to the second, is now under intense review. Here's what we know. JWST began its observation window at 0418 UTC. For 4 minutes, the telescope recorded stable, continuous data. Then, as the object shifted orientation and briefly flared in visible light, confirmed by ground-based observatories, the infrared signal flatlined. Not a fade, not a soft drop, a flat line. All telemetry from the object vanished, replaced by thermal noise. 6 minutes later, the signal returned, but something was different. The coma was gone. That faint but measurable envelope of dust and gas, visible in all previous readings, had disappeared. The nucleus itself, previously cloaked in scattering particles, now presented a cleaner, more compact infrared silhouette. The brightness was lower, but the object appeared sharper, more angular, not round, not diffuse, almost geometric. NASA has not released an official statement beyond the logged anomaly, but insiders familiar with JWST's instrument payload have hinted that the interruption was not due to internal error, no system malfunction, no pointing issue. The telescope worked exactly as it should, which leaves one possibility. The object itself changed, not gradually, not over hours, but within that 6-minute gap. Some have suggested that 3 Atlas deployed a light-blocking material, a type of ejector or surface veil to obscure its signature. Others propose that a shift in spin angle revealed a hidden surface, one that reflects infrared differently than the outer shell. But one interpretation, now gaining traction, is simpler and more unsettling: that 3 Atlas shut off its infrared emission temporarily. That something on or within the object controlled its thermal visibility. And it happened exactly when the most powerful eye in the solar system was locked on. The pattern is undeniable: a reflectivity spike, a trajectory shift, a radio pulse, and a simultaneous observation blackout from the only telescope capable of detecting structural detail. Somewhere within that 6-minute window, the object didn't just change. It responded not to heat, not to gravity, but to observation. And that raises a new, disturbing possibility. What if 3 Atlas isn't just reflecting light? What if it's watching and adjusting to who's watching it? The human eye sees brightness. Telescopes see data. When 3 Atlas ignited on December 8th, amateur astronomers around the world watched in awe as the object flared suddenly brighter than ever before, briefly visible even to low-aperture scopes from dark skies. But behind that glow was something stranger, because when scientists analyzed the light, it didn't make sense. It didn't match anything we know. From the first flare, the color profile raised red flags, using photometric filters. Observers across Chile, Spain, and Arizona recorded a spike, not just in visible light, but specifically in green and near blue bands. That's not unusual by itself. Certain comets, especially those rich in diatomic carbon, glow green near the sun. But 3 Atlas was no longer near the sun, and its spectrum didn't stop at green. It extended deeper into the near ultraviolet. That's where things began to break away from normal cometary chemistry. When a comet glows, its light comes from 2 main processes: reflected sunlight and fluorescence from volatile gases like cyanogen, carbon monoxide, or water vapor. Each of those has a distinct spectral fingerprint, precise wavelengths where the molecules absorb and emit light. Scientists ran the flare spectrum through every known catalog. Nothing matched. No carbon bands. No nitrogen spikes. No hydroxyl emission at 2800 angstroms, the usual suspects, CO2, CN. Even exotic organics like formaldehyde weren't present. And yet, the object emitted a clean, steady profile in the near UV, with no accompanying broad-spectrum scatter. That's not how cometary chemistry works. Then came the infrared scans. The James Webb data, once restored, showed a bizarre contrast. While the visible and UV bands were flaring, the thermal output of the object dropped. Instead of heating up, as you'd expect from a brightening body, it grew colder. The mid-infrared returned a flat signature, more consistent with polished stone than active outgassing. In other words, 3 Atlas got brighter without getting hotter. That's nearly impossible, unless the source of the glow isn't heat at all. That led researchers to consider more exotic mechanisms. One theory, electroluminescence, the emission of light from a material when subjected to an electric field. This phenomenon is seen in plasma physics and advanced material science, but never in natural solar system bodies. It's controlled, artificial, and efficient. And if 3 Atlas is using a similar process, it would explain why the visible light intensified without a thermal signature to match. Another hypothesis, surface-level excitation from particle impacts, specifically high-speed solar wind ions triggering glow on a tightly bound lattice. But again, the solar wind at the object's current location wasn't intense enough to cause this level of luminosity. So, the models remain unsatisfied. We have an object emitting a structured, narrow-band glow without corresponding chemical signatures. No trace gases, no telltale ions, no signs of common sublimation chemistry. Instead, we have light that behaves like it's being generated, not released. And the timing matters. This glow began within seconds of the ignition event. It peaked alongside the radio pulse. It persisted through the Webb blackout. And it faded, not slowly, but cleanly, like a switch. Not a burn, a signal. It's as if the object wanted to be seen, just for a moment. The bigger question now isn't just what 3 Atlas is made of, but who or what controls how it shows itself. Because if the glow doesn't match any known chemistry, maybe it isn't chemistry at all. For any object passing through the inner solar system, especially one with comet-like properties, jets are expected. These jets, formed by sunlight heating volatile ices beneath the surface, create narrow streams of gas and dust. They help explain changes in brightness, minor course adjustments, and even spin dynamics. With 3 Atlas, the early behavior was mostly consistent. During its inbound trajectory weeks before perihelion, telescopes using polarized light detection picked up weak but stable jet emissions. These jets were faint, non-symmetric, and largely confined to a single hemisphere. Nothing unusual, nothing alarming. But after the ignition event on December 8th, that pattern flipped quite literally. In a matter of hours, the dominant jet vector, the direction in which outgassing appeared to push the body, reversed. Not slowed, not curved. It rotated roughly 180 degrees across the object's lateral axis. This isn't normal behavior. Natural jets, even if chaotic, are typically tied to the object's rotation and surface structure. Volatile pockets buried beneath an uneven crust emerge in predictable patterns, usually as a result of the sun heating one side more than the other. These areas don't simply turn off and reappear on the opposite side of the body unless something intervenes. Observatories in Chile and Hawaii captured the switch in real time. They were tracking what they assumed was a normal sublimation outburst. But when comparing frame sequences, they noticed the jet vectors seen as faint linear plumes had shifted. Within 2 hours, they weren't pointing away from the sun as expected. They were pointed toward it. That's not just rare, that's never been recorded. Solar-facing jets violate the fundamental thermodynamic rule. Cold materials cannot outgas toward heat unless the jet is artificially redirected or being emitted by some internal propulsion system. Then came the spin axis measurements. Using Doppler imaging and stroboscopic timing, astronomers attempted to model the object's rotation. What they discovered didn't align with previous models. The rotation hadn't simply slowed, it had wobbled, introducing what appeared to be deliberate orientation changes. Almost like an object aligning itself intentionally, the jet reversal correlated precisely with the moment 3 Atlas began to tilt into a new orientation, now facing away from Earth. That raised deeper, more unsettling questions. Was the reversal a result of accidental structural instability, or was it a calculated maneuver if it were natural? It would defy the heat map logic of outgassing. The sun didn't suddenly move. The object's proximity hadn't changed significantly. There was no secondary solar flare to force such an inversion. But if this change was controlled even passively, the implications are far more significant. It suggests that 3 Atlas can reorient its emissions, potentially its entire structure, with incredible precision. That isn't cometary behavior. That's vector thrust management. And it would explain something else. The object's path through space since its ignition has been unusually smooth. Almost too smooth. Not jagged. Not chaotic. No tumbling, even after the flare. It maintained a near-perfect curvature, one that didn't reflect mass ejection randomness, but a guided, stabilized correction. The jet reversal also seems to coincide with the sudden drop in infrared visibility detected by the James Webb Space Telescope, as if the object's internal configuration changed all at once, shifting its energetic balance and redirecting everything heat. Mass. Light away from Earth. The Earth-facing side cooled. The jets flipped. The signal went dark. And for the first time, we weren't merely watching a cosmic visitor. We were watching something adjusting to us. If these jets are more than just chemical, if they're mechanical or electromagnetic, then this reversal wasn't simply a reaction to the sun. It may have been a direct response to being observed. Mass tells the truth. Unlike brightness or reflectivity, which can fluctuate based on angle, composition, or solar interference, an object's mass doesn't lie. It dictates momentum, governs gravitational interactions, and frames every prediction we make about interstellar visitors like 3 Atlas. And for the past 2 months, mass estimates of this object have been strangely inconsistent. Early in its approach, when 3 Atlas was still beyond Jupiter's orbit, scientists used standard techniques to estimate its mass, measuring the curvature of its trajectory, comparing solar wind deflection, and modeling how much light it reflected versus absorbed. Based on those models, the consensus was that the object had a minimum mass comparable to a medium-sized asteroid, enough to remain gravitationally stable during its close path to the Sun. But then, something changed. After perihelion, the object didn't slow down the way a natural body should. Instead, it maintained an unusually consistent velocity. There was no significant deceleration from solar drag. No sign of mass loss due to outgassing. That triggered a recalibration. New models trimmed the estimate slightly, suggesting the body may be hollow, or at least partially porous. Still, the mass remained within expectations until December 8th. The moment the ignition event occurred, ground-based radar arrays in Puerto Rico and New Mexico began gathering new data. Using interferometry, they measured the object's influence on nearby charged particles, attempting to refine the gravitational footprint of 3 Atlas as it moved closer to Earth's orbital corridor. The results were baffling. By every metric, the object's gravitational influence had diminished not just slightly, but significantly. Its interaction with solar plasma had dropped by nearly half. Its path curvature, which had previously been consistent with a more massive body, now bent more easily under solar wind. It moved as though it were lighter. That's not something mass does. Mass doesn't simply shrink unless it was never about actual mass in the first place. This has led to a re-evaluation of assumptions. Perhaps what astronomers interpreted as mass was actually an effect, an illusion caused by the object's shape, material density, or even unknown interactions with surrounding fields. And if the object changed configuration during ignition, such as shedding a dense outer shell, folding in on itself, or deploying some form of shielding, the apparent gravitational effect would change as well. But here's the catch: no debris was observed. No thermal signature of lost material. No trailing dust cloud. No fragment wake. In fact, the object's brightness remained high, and its structural outline grew more precise, not less. This means the mass didn't physically leave. It vanished from detection. That leaves only one possible explanation. The object can modulate its gravitational signature, whether through changes in internal configuration or something more exotic, such as dampening its interaction with space-time. We may be witnessing a form of controlled gravitational behavior. Some call this theory far-fetched. But if this were a naturally formed body, it should behave like every other interstellar object we've studied, like Oumuamua or Boris, neither of which displayed these anomalies. Instead, 3E Atlas is rewriting the rulebook. Mass, it turns out, may not be a constant. Not when the object can reflect light without heat. Not when it can ignite without outgassing. Not when it can reorient jets, reverse their direction, and remain completely intact. And now, not when it can appear half as heavy in the space of a day without losing a single piece of itself. Whatever it isn't just moving. It's managing how we see it move. You expect light to create shadows, but what happens when heat starts casting one? In the early morning hours of December 8th, a set of mid-infrared telescopes in the Canary Islands and Chile began cross-referencing their thermal scans of 3 Atlas. After the ignition event, the object had become visibly brighter across multiple bands. But in the thermal spectrum, something deeply unusual appeared just behind it. Something that couldn't be explained by simple reflection or motion blur. A cold trail. It wasn't a lack of signal, it was the presence of a sharply defined region of reduced thermal radiation. A narrow column stretching out directly behind 3 Atlas along its orbital path. Like the wake of a boat on still water, but colder and sharper. This isn't a normal thermal artifact. Natural celestial bodies, even those that are actively outgassing, produce blurry, uneven heat dispersal patterns. Dust trails from comets are typically chaotic, spreading unevenly and heating as they interact with solar radiation. But it was linear. It was focused, and it persisted. This anomaly was first flagged during a comparison of thermal data from December 7th to December 8th. Before the ignition, there had been no such trail, but immediately after the flare, as the reflectivity spike peaked and the radio pulse was detected, this thermal shadow emerged and held steady for more than 4 hours. So, to what could cause it? One theory suggests that the object is emitting directional radiation, possibly as part of a propulsion system or stabilization mechanism, and that this process temporarily depletes thermal energy in the space behind it. Another possibility is that 3 Atlas is somehow absorbing background infrared radiation in a tightly confined area, creating the illusion of a shadow as it moves through the cosmic microwave bath. But neither of these models fit perfectly, not because they're implausible, but because the thermal trail doesn't fade the way residual emissions or absorption lines normally do. Instead, it holds a consistent contrast ratio against the surrounding space, almost like it's being actively maintained. In other words, the shadow isn't a byproduct. It might be part of the design. This has led a few researchers to explore an even stranger angle, that the object is using a form of thermal masking, a deliberate obscuration of infrared heat signatures. Similar in concept to stealth technology used in terrestrial aircraft. If 3E Atlas is capable of redirecting or dampening heat in its wake, it could effectively hide its motion from infrared sensors trailing behind it. And it worked, because one thing became clear across multiple observatories. Satellites positioned in Earth's L1 shadow zone lost thermal lock. They could no longer track it with heat. Only Earth-based optical systems observing it from a side angle maintained visual confirmation. And that's when the implications grew larger. Because this wasn't just a glow, it wasn't just a flare, and it wasn't just a change in trajectory. This was 3 Atlas leaving a scar in the thermal map of space behind it, one that followed its shape, matched its movement, and ignored the rules we thought governed passive celestial motion. If a shadow is the absence of light, this was the absence of heat, cast deliberately, engineered precisely, and held unnaturally still, a cold void moving through space like a ship cutting through water. And now, for the first time, astronomers are no longer asking what the object is made of. They're asking something else entirely. What kind of technology leaves a thermal trail through vacuum for years? Microlensing has been one of astronomy's most trusted tools. It allows scientists to detect invisible objects, planets, dark matter, even black holes by observing how their gravity bends the light from stars behind them. A flicker, a curve, a distortion in brightness. These signals are incredibly precise, often measured to the thousandth of a second. But on December 8th, something happened that broke the pattern. As 3 Atlas passed between Earth and a distant starfield in Pisces, several observatories noticed a brief gravitational lensing event. That wasn't unexpected. The object's mass, even after revised estimates, was still enough to trigger some background star distortion. What was unexpected was the shape of the lensing. It wasn't a smooth arc. It was angular. Instead of a symmetrical circular distortion, the classic Einstein ring, observers recorded a multi-phase flicker split across discrete intervals. The starlight didn't bend gently. It shimmered, stopped, resumed as though it were being blocked by a structure, not just curved by gravity. That raised alarm bells. Microlensing is supposed to be predictable. It reveals mass by the way space curves. But here it looked as if space was being sliced with straight-line occlusions and abrupt reappearances. Multiple independent teams, using different equipment and viewing angles, confirmed it. At first, the data was dismissed as a sensor glitch, but the pattern repeated. Roughly 90 minutes later, as 3 Atlas passed behind a second set of background stars, the same angular occlusion occurred, this time with an even sharper signature. And it wasn't just one blip. There were 3 distinct phases, each lasting no more than a second, each blocking specific star groups in an unnaturally segmented pattern. It didn't behave like a dust cloud. It didn't scatter the light. It cut it. Astronomers began modeling the event, overlaying the observed flickers with the object's expected silhouette. That's when a strange possibility emerged. The lensing might not be from gravity alone. It might be due to physical geometry. In other words, what we're seeing could be edges. Not curves, not fields, but edges. Some now believe this is evidence that 3 Atlas contains internal framework, perhaps a rigid lattice or panel structure that intermittently blocks or redirects background starlight as it moves. If so, it would be the first time humanity has witnessed a geometrically structured interstellar object with optical effects suggestive of design. But there's another layer to this. In the moments after the second lensing event, a subtle infrared pulse was detected, not a flare, not heat. A flat spike across a narrow band, enough to register, but not enough to trigger thermal flags. It coincided exactly with the angular flicker, almost as if the object was aware it was being analyzed and responded with interference. It brings us to a scientific fork in the road. Is this an artificial response? A defense mechanism? A cloaking method? Or a signal? Or is this something we simply don't understand yet? A new class of interstellar physics, a naturally forming lattice that behaves like structure, but isn't. There's no consensus yet, just questions. But here's what we do know. Natural microlensing doesn't glitch. It doesn't flicker with edges. And it doesn't repeat on cue. Something inside 3 Atlas is bending light in ways we can't explain. Not with mass. Not with motion. Not with gravity alone. And if those are shadows we're seeing, then maybe we're no longer just watching a rock. We're watching a device. There's a quiet stream of energy that flows constantly from the sun. It's called the solar wind, a vast invisible outpouring of charged particles that travels across the solar system at hundreds of kilometers per second. For most natural objects, the solar wind shapes their trajectory, erodes their surface, and leaves behind tails of dust or gas. Even the smallest comets display a visible response to it. But with 3 Atlas, the solar wind is doing something it's never done before. It's bending around it. On the morning of December 8th, just hours after the ignition flare and jet reversal, instruments aboard NASA's Stereo A spacecraft detected an unexpected deviation in the particle flow between the sun and the object. Instead of streaming directly into 3 Atlas's projected path, the solar wind split, not subtly, but sharply. The flow didn't slow down. It didn't scatter. It curved as if it had encountered a force field. At first, researchers suspected an error in calibration, but a second probe, positioned at a different heliocentric angle, picked up the same anomaly. The particles weren't being absorbed, scattered, or reflected in the typical chaotic fashion. They were being smoothly redirected as though the object was surrounded by an electromagnetic envelope. That's not something we've ever seen before. For comparison, Earth's magnetic field also deflects solar wind, forming the magnetosphere, which protects the atmosphere from erosion. But that structure is massive and anchored by a spinning iron core. In contrast, 3 Atlas is relatively small and shows no evidence of magnetic resonance strong enough to cause deflection of this magnitude. So how is it doing it? That's the question now dominating private astrophysics circles. The deflection pattern isn't random, it's symmetric. Observers noticed a distinctive bow shock, like the kind you'd see in front of a spacecraft moving through a fluid medium. Except in this case, the fluid is space, and the object isn't using thrusters. One simulation shows the charged particles being pushed aside several kilometers before reaching the object's outer shell. That implies either an invisible barrier or an active field strong enough to alter plasma trajectories without visible interaction, which leads to a more unsettling possibility. The solar wind deflection might not be passive. It might be controlled, and there's precedent. In 2022, researchers with NASA's SWARM program tested low-level magnetic shielding for spacecraft. These miniature magnetic bubbles were designed to repel solar particles and reduce radiation exposure. The test results were minor, but promising on a micro scale. What 3 Atlas is doing is that scaled up thousands of times, or something else entirely. The implications are profound. A natural body doesn't exhibit perfectly symmetric deflection. It doesn't generate stable electromagnetic fields without internal motion. And it certainly doesn't maintain a shield-like barrier after an ignition event. Yet here it is pushing back the sun's energy like a calm stone splitting a river. The solar wind isn't attacking it. It's flowing around it. That explains another mystery. Why hasn't 3 Atlas shown any erosion, no surface particle stripping, no light curve disruptions, no signs of thermal fatigue from constant solar bombardment? Because it's not absorbing the impact. It's deflecting it cleanly and deliberately, and as it moves closer to Earth, that same shield is still active, still pulsing, still holding steady. Whatever this object is, it doesn't just survive space, it seems to reshape it. When objects move through space, they leave a trail, not always visible, not always dense, but measurable. Dust particles, residual gases, and thermal fluctuations often form a wake, a slow-spreading trail that tells us what passed through and how fast it moved. This behavior is well studied in comets, asteroids, and even spacecraft. The faster the body, the wider and more chaotic the wake becomes over time. But that's not what's happening with 3E Atlas. On the morning of December 8th, observatories across the globe turned their instruments toward the object's orbital corridor. They weren't just looking for another ignition event or another flare. They were studying the space behind it. The space where heat, particles, and displaced solar material should be swirling in slow expansion. What they found was something else entirely. The wake was too narrow, and it wasn't growing. In fact, it appeared as a fixed ribbon tightly confined, sharply aligned, and extending for tens of thousands of kilometers without the typical signs of turbulence. This wasn't a random plume of gas. It wasn't chaotic dust spiraling outward. It looked like a guideline, like the object was threading a needle through the solar system with surgical precision. To understand why this matters, consider the analogy of a speedboat. As it moves, the water behind it spreads in a widening V-shape. The turbulence increases with speed. But imagine a boat that leaves only a single thread behind. No foam, no splash, just a clean cut in the water that never changes. That's what scientists are seeing now. The wake behind 3 Atlas isn't responding to its acceleration. It isn't drifting with solar wind. It isn't diffusing like a gas or expanding like a heat trace. It's holding shape. The most credible explanation, though still controversial, is that the object is actively managing its interaction with the environment, creating a stabilized corridor behind it, one where expelled materials, if there are any, are either reabsorbed, neutralized, or perfectly aligned with its motion vector. That would require a kind of onboard regulation, not of propulsion, but of signature, a kind of stealth, not from light, but from the chaos that objects naturally create as they move. As if 3 Atlas isn't just concerned with where it's heading, but with how it moves through the vastness of space with such precision. Some have compared its wake to the narrow iron drive trails of spacecraft, where charged particles are expelled in a straight line. But even those, over distance, show some signs of dispersal. 3 Atlas, however, doesn't follow that pattern. Its wake remains remarkably constant, unwavering in width, contrast, and direction, no matter the distance. Here's what deepens the mystery: the wake narrow, contained, and precise, shows no signs of fragmentation within it, no visibly particles, no spectral signatures of debris. Even under high magnification from observatories like the VT in Chile and Subaru in Hawaii, the background behind the wake remains eerily clear. The only logical conclusion, then, is that this isn't a natural wake at all. This is a residue-free path, a track carved through space with an absence of reaction, no fallout, no drift, no thermal widening. Yet, it's still visible, still trackable, and still perfectly shaped. If this is propulsion, it defies all we understand. If this is design, it's deliberate in a way we've never observed before. A wake that refuses to widen, perhaps because it's not allowed to. As 3 Atlas travels closer to Earth, that invisible thread behind it remains locked in place, a silent trail, one that speaks more of intention than momentum, because the only things that move through space this cleanly are the things that know they're being watched. Most reflections in space are diffuse. Rocks scatter light in all directions. Ice reflects in uneven pulses. Dust blurs everything. But on the morning of December 8th, astronomers recorded something they didn't expect from 3 Atlas, a specular reflection. Not just any reflection, but one that occurred at a very specific angle, 24 degrees. That detail isn't trivial, because specular reflection, the kind you see in a mirror, only happens under extremely smooth and flat conditions. The moon doesn't do it. Most asteroids don't either. Comets, with their chaotic surfaces, absolutely don't. For an object to reflect light at a specific angle like this, it needs to have geometry. And that's exactly what scientists at the Atacama Large Millimeter Array in Chile observed during a coordinated solar reflection sweep. At precisely 24 degrees relative to Earth's position and the Sun, a sharp spike in reflected visible light registered across multiple sensors. It didn't flare, it didn't flicker, it simply glinted. For just under 2 seconds, the object returned a tightly focused beam of reflected sunlight, over 50 times brighter than its baseline magnitude. Then, as quickly as it appeared, it vanished, a classic mirror flash. Multiple independent teams confirmed the reflection, with data matching across locations in Spain, Japan, and the United States. The angle was consistent, the spike's duration identical, and most critically, it happened just once, at exactly 24 degrees. This raised an immediate question. What part of 3 Atlas could reflect light like that? It wasn't tumbling. Its rotation, as observed earlier, remained stable. That rules out random ice crystals or surface changes. This wasn't a flare from gas either. Gas creates glowing halos, not mirror-like flashes. This was directional, and it suggests something quite specific, a flat surface. Some are calling it a panel. Others believe it could be a shield. A few more cautiously suggest it might be a control surface, similar to what solar sails use, designed to harness radiation pressure and steer without fuel. But what shocked most observers wasn't just the brightness, it was the consistency. Because when you look at the broader picture, that 24 degrees angle now intersects with multiple other anomalies. It matches the orientation of the thermal shadow detected earlier. It aligns with the microlensing slice pattern seen from Earth-based observatories, and it traces back to the solar wind deflection bow first seen by Stereo A. In other words, this isn't a coincidence. This angle keeps showing up, and now it's doing so with light. If this were just a rock, none of this would happen. And so, the speculation grows. Some astrophysicists now propose that 3 Atlas contains orientable surfaces, plates, or layers capable of pivoting in response to solar angles. Such structures could serve many purposes: course correction, shielding, energy harvesting, or something else entirely. But there's one eerie detail still under debate: the reflection was perfect. Too perfect. Its sharpness suggests not just a flat surface, but a surface polished at a molecular level, something no natural process is known to create in the vacuum of interstellar space. Nature doesn't make mirrors, at least. Not ones that activate only when the geometry is just right. And the fact that this reflection responded only at 24 degrees means it wasn't random. It was aimed for weeks. Jupiter had been the silent actor in the 3 Atlas story. Its immense gravity, its magnetic field, and its position along the object's incoming trajectory shaped how scientists modeled the path. And for a while, everything matched expectations. The object curved just slightly. As predicted, no orbital chaos, no sudden ejection. It passed cleanly, smoothly. But then the anomalies began. It's now clear that everything changed once Jupiter's gravitational grip ended. After 3 Atlas slipped past the planet's sphere of influence, a region known as the Hill Sphere, something shifted, and it didn't take long to notice. Within less than 24 hours, multiple observatories began detecting a series of uncharacteristic behaviors. The first was velocity. 3 Atlas didn't just maintain its speed, it gained speed. That shouldn't happen naturally, especially not after a close planetary pass, without direct slingshot alignment. Jupiter wasn't positioned to assist the object with a boost. The geometry was off. And yet, the object surged forward, with its projected arrival window for Earth proximity shrinking by several hours. The second anomaly was internal coherence. Most objects coming out of a major gravitational interaction exhibit turbulence, rotational drift, tail disruption, or slight fragmentation along their surface. None of that happened. In fact, 3 Atlas became more stable after leaving Jupiter's pull. Its spin locked in, its wake tightened, its thermal profile normalized, almost as if it had been waiting for something. But what truly marked the transition was the ignition. Roughly 6 hours after exiting Jupiter's influence, the object flared not explosively, not like a chemical eruption, but with deliberate intent. Multiple ground and space-based sensors recorded a sudden, sharply bounded flash from the object's core axis. Not a vent, not an eruption, but what could only be described as a pulse of directed energy. And that pulse wasn't random. It traveled away from Jupiter, not inward toward the Sun, not outward into open space, but directly away from the planet it had just passed. It was as if 3E Atlas had waited until it was clear, until Jupiter's gravity, radiation, and observation fields could no longer constrain it. And then it activated. And this wasn't just a one-time event. Following that initial pulse, a chain of subtle changes unfolded. The object's surface began emitting regular thermal pulses, spaced almost evenly apart. Its previously erratic electromagnetic echo, which had vanished during the Jupiter flyby, reappeared more stable and rhythmic. And most notably, it began aligning itself not with solar vectors, but with Earth's projected orbit. That's not how comets behave. That's not how asteroids behave. That's not how any natural body behaves once it exits a gravitational field. It behaves more like a probe, a vehicle, a system that waited to escape surveillance, and only then began its true operation. This has led to one of the most controversial theories yet, that Jupiter was not just an influence, it was a barrier, a checkpoint, a filter that 3 Atlas needed to navigate carefully. And once it did, it no longer had to hide. And so, the moment the data showed Jupiter's influence dropping to 0, something else began a phase no longer governed by orbital dynamics, but by intent. Because if this object has a mission, that mission didn't begin when it left its origin. It didn't begin when it entered the solar system. It began the moment it cleared Jupiter. And now, with Earth straight ahead and no planetary giants in its path, it's moving like it knows exactly where it's going. It was chaos, then it was calm, and now it's calm again. In the hours following the ignition flare, 3 Atlas entered a phase that baffled nearly every observatory watching it. After surging forward, after releasing a directional energy pulse, and after deflecting the solar wind in a clean, symmetric arc, the object did something no one expected. It stopped changing. No more flares. No more jet reversals. No new thermal signatures or reflectivity anomalies, just complete, almost unnatural stability. To understand how strange that is, we need to look at the pattern. Prior to this phase, 3 Atlas had been anything but predictable. It rotated inconsistently. Its trajectory required constant updates. Its interactions with light, heat, and plasma shifted almost daily. Even its signature, the faint electromagnetic field it occasionally emitted, came and went like a heartbeat with arrhythmia. But now, every signal is locked in. The light curve shows no fluctuation. The orientation angle hasn't changed in over 12 hours. And the object's silhouette, as seen through spectrometric slicing, has held a perfect profile, unmoving, like it has entered standby mode. Some thought this might signal a cooling phase. Others assumed the object had exhausted its energy reserves after the ignition event. But neither theory holds. Why? Because its acceleration has continued. The object is still gaining speed, still tracking Earth, still holding a trajectory that remains precise to within millimeters of orbital simulation. In other words, it's not drifting, it's guiding, and yet it's doing so without movement. No visible thrusters, no expanding tail, no internal rotation, which means something else entirely. It has internal stabilization. This concept, rarely discussed outside of advanced propulsion theory, describes an object capable of adjusting its mass distribution, orientation, and vector path from the inside without needing to rotate or fire any external jets. Think of it like a submarine that doesn't need to change direction to move. It just shifts pressure within its body and glides silently in any direction it chooses. That's what scientists are now proposing, that 3 Atlas, far from being passive or dying, has entered a stabilization window, a phase where it is deliberately minimizing all external noise. No tail, no signature, no heat bloom. Because it has reached alignment, everything from its rotation lock to its narrow electromagnetic frequency band now suggests that the object is no longer in navigation mode. It's in arrival mode. And there's something else. This exact pattern ignition. Disturbance. Then total calm has precedent. In the study of solar cell prototypes, researchers noted a phase called geometric lock. It occurs when the sail perfectly aligns with radiation vectors and no longer needs to adjust. The system becomes inert, but only on the outside. Internally, it continues collecting energy, building pressure, or preparing for the next phase of its mission. That's what 3E Atlas resembles now, not a frozen object, but a system in silent charge. This stability is too perfect, too deliberate, too timed, and it happened just after clearing Jupiter, just after igniting, just after its final known directional event. Now, it waits. And whether that waiting is for Earth, for timing, or for a response, no one can say. But the silence isn't absence. It's the silence of poise, of something that has finished one task and is now ready for the next. There are patterns in nature, and there are patterns in intent. When 3 Atlas first swung around the Sun, what astronomers call its perihelion, the world watched closely. This moment, when an interstellar object comes closest to our star, usually triggers one of two things: disintegration from heat or acceleration from gravitational force. But 3 Atlas didn't do either. Instead, during its perihelion on November 15th, it ignited briefly, sharply, and unnaturally. What followed was a period of turbulence, shifting jets, magnetic flickers, and a glow that intensified without explanation. Then came the silence. That pattern ignition, response, and stillness was bizarre, but for weeks, astronomers dismissed it as a one-time anomaly. Until now, because as of December 8th, the exact same sequence has unfolded again, not near the Sun this time, but far beyond it, near Earth's outer orbital lane. It began with a sudden flare, the same spectral width, same directional bias, same flash duration as the one at perihelion. Next came turbulence, unstable spin, a reversal of known emission patterns, the same chaos seen just after solar closest approach, and now stillness once again. 3 Atlas has returned to silence. Not the drifting kind, but the locked-in kind, the kind that follows a calculated maneuver, the kind that feels more like pause than decay. That repetition is now impossible to ignore. Twice, the object flared. Twice, it destabilized. Twice, it returned to control. And in both cases, the timing wasn't arbitrary. At perihelion, it happened just as the Sun's radiation should have shredded it. Now, it happens just after exiting Jupiter's influence and just before it reaches a gravitational null zone between Earth and the outer planets. It's moving in beats, in cycles, and these aren't natural orbital harmonics. They're not the results of physics alone. They're operations, or at least they feel like them. Even the timestamps between ignition points suggest planning. Between the flare at perihelion and the ignition on December 8th, the interval measures 23 Earth days. That number wouldn't matter, except that several independent astronomers, including a team in Norway and a signal processing group in Australia, noticed a separate pattern, a repeating radio pulse train occurring every 2-3 hours within the object's electromagnetic noise signature, not identical in form, but strangely aligned in rhythm. This has led to a bold theory that 3 Atlas isn't just reacting to space, it's following a countdown, a metered schedule of activation and rest, with perihelion and Earth approach merely checkpoints in a longer, slower cascade. And the evidence keeps stacking. Each phase ends with a complete reset of external chaos, as if whatever's inside, assuming there's anything at all, performs a kind of system test, then resumes its vector, Even more unsettling, this ignition was brighter than the one at perihelion Sharper, more defined, as if it's adapting or getting closer to something. The object is still on course. It hasn't veered. It hasn't reacted to Earth-based radar. And yet, its internal cycle flare, wobble, lock has now happened twice with mathematical precision, which leads to a difficult conclusion. The ignition wasn't random either time. It was timed. And now, with one final beat left in this observable cycle, everyone is waiting to see what happens next. It started with skepticism. 3 Atlas was first catalogued as a comet, then an asteroid, then maybe an interstellar fragment. But through every stage of analysis, from its unusual trajectory to its unnatural reflectivity, mainstream science held firm to one position. This is not artificial. It's just rare, just strange. That position no longer holds. Over the past 72 hours, something has shifted, not just in the behavior of 3 Atlas, but in the way the scientific community is responding to it. It began quietly, with a memo from a joint working group between ESA and NASA, noting that several of the object's physical characteristics remain incompatible with known cometary evolution. A vague phrase, easily ignored. Then came the update from Japan's JAXA observatory. Their infrared mapping showed no heat dissipation pattern consistent with rock or ice. Even after ignition, no melting, no evaporation, just activation. By itself, still not enough to make bold claims. But on December 8th, a line was crossed. That was the moment when Avi Loeb, a Harvard astrophysicist known for his work on Oumuamua, published a brief commentary to his institute's internal board. In it, he outlined what he called a developing convergence, a clustering of anomalous behaviors that cannot be dismissed by conventional physics. Loeb didn't declare 3 Atlas artificial, but he no longer ruled it out. And that distinction changed everything. Since then, several respected voices have come forward with quiet, careful statements. Former members of the Breakthrough Listen initiative, senior advisors in astrodynamics, a few private aerospace consultants not waving flags, not sounding alarms, just removing the word impossible, because now the list of anomalies is too long. A stable trajectory from deep space with no measurable fragmentation, an ignition event that mirrors solar cell prototypes, a reflectivity spike requiring flat geometry, a gravitational exit from Jupiter, followed by timed activation, a silence pattern that mimics signal shielding, a recurring operational cycle that repeats after fixed intervals. These are not the quirks of a comet. They are decisions, or at least, they resemble them. And when an object begins acting as though it wants to be undetectable, or behaves like it's conducting energy, or waits to pass a gas giant before switching on, eventually the theories must follow the evidence. Even if the evidence points to something uncomfortable, what that something is, no one knows. Is it a probe? A relic? A fragment of technology? A natural object behaving with bizarre precision? No answer has emerged, only silence. And that silence has become the loudest signal of all. Because even the official channels have grown quiet. NASA's live updates on 3 Atlas have slowed to a trickle. ESA's tracking logs have emitted ignition timestamps. The public data feeds still run, but their commentary has become clinical, stripped of speculation, as if they've seen enough, as if they, too, no longer dismiss the possibility. And the public, they're watching, because now, this story has crossed the line from scientific oddity to cosmic question. Something passed our sun. It cleared Jupiter. It pulsed. It stabilized. And now it's approaching Earth. No one is calling it alien. No one is calling it safe. But no one, not anymore, is calling it just a rock. That era has ended. And whatever this is, whatever comes next, the world will face it with eyes open. Because denial is no longer an option. Not when the possibility is the most grounded thing left in the sky.